All right, welcome. Let's get this video started. Today's video is on conic sections, and it's going to be, again, a crash course of conics. We did not have time to go through the chapter lesson by lesson, one each day. So I'm going to give you a big kind of large-scale overview of what conic sections are. Why are they called conic sections? Their equations, their graphs, and how to put them in standard form and find out various pieces of information about them. So let's start with what conics are. Conic sections are shapes that can be formed from slicing cones in different ways. And there are four main ones we talk about. They are on the screen right now. Parabolas. Right there, you see a parabola. And I'm hoping you can see if you take a blue, we could call that a sheet of metal, and slice a cone right there, you can kind of see that it's going to form the parabolic shape that we're somewhat familiar with. So parabolas are conic sections. There are also circles, and that one's fairly easy to see. We slice this cone straight across, it will create a perfect circle. Ellipses are kind of like circles, but they are circles that are stretched. They're ovals, basically. And so ellipses are our third conic section, followed by hyperbolas, which are interesting conic sections. You slice this kind of double-sided cone, and you can see it's going to create these, they almost look up close like two parabolas facing away from each other. They're actually not parabolas, but two-part graph known as a hyperbola. So conic sections are created by slicing a cone at different angles, different parts of the cone. And this is the order that we're going to go through them. So let's start with parabolas. We've already seen parabolas quite a bit in chapter 5, but we only saw upward facing and downward facing parabolas. There are actually also parabolas that open to the left and to the right as well. Now, in the back of your mind, you might be saying, wait, something doesn't seem right about that. They don't pass the vertical line test. You are correct. These parabolas are not functions per se, but they are conic sections. We can graph a sideways parabola there. So a couple of things just with the chart on the screen right now. First one, the vertex, you will notice, of all four of these parabolas, no matter which way it faces, the vertex is always considered h comma k. Those are the variable names that we're going to use to represent the x and y coordinates of the vertex. Now, I want to look at these equations. When a is positive, and we have this equation, y equals a times x minus h squared plus k, our parabola opens up. We actually saw that equation back in chapter 5, and it's called vertex form. In conic section parlance, that's called standard form, but y equals a times x minus h squared plus k. If a is greater than 0, it faces up. If a is less than 0, and y is on that left-hand side by itself, it faces down. Now, what about, I'm going to change colors real quick. What if a is positive? Turned green on me. What if a is positive and x is by itself on the left-hand side? Look at that equation in the bottom left. X equals a times y minus k squared plus h. So a few things got flipped around there. The x and the y switched, and notice also the inside of the parentheses. It was x minus h squared. So x minus h, x minus the x coordinate of the vertex. Now it's y minus k, y minus the y coordinate of the vertex. So a lot of the x's and y related values got flipped around. If x is by itself and y is the squared part, it's going to open up sideways. And if a is positive, then we're opening in the positive x direction, the right. Whereas on the other side, if a is negative over here and x is by itself, that means we are opening in the negative x direction, opening to the left. So a couple key points just about parabolas there. And what I would like to do is just take you through one problem where we write the equation in standard vertex form. Identify the vertex, the axis of symmetry, and the direction of opening of the parabola. Well, just from this, I'm hoping you can see, just looking at the equation, x is by itself, y's are being squared. When x is by itself, that means it opens to the left or the right. And because we have positive y squareds here, I know for a fact that it's going to open right. It's going to open in the positive x direction. So direction of opening, check. How do we get this into vertex form, standard form? Well, it's going to involve completing the square. And this is going to be a theme through this entire Conics Crash Course. Let's complete this square. It's been a while since we've done that, so let me remind you of a couple things. First one, I'm going to go x minus 6. I'm going to get that constant out of there. Leave a really blank space, y squared minus 6y. And I'm going to put plus blank plus blank. Now, I need to make the right-hand side of that equation a perfect square. I need to make it y minus something squared. So how do we figure out what goes in the blanks? It's always b divided by 2 squared. And I'm hoping that's ringing some bells. B is the number of y's we have. So divided by 2 would be -3 squared equals +9. I need to add 9 on both sides. So completing the square is not a new skill. It's something we have looked at, have studied, but now we're doing it to put these conic sections in their proper form. So what does that mean? On the left-hand side, we have x plus 3, if we combine like terms, equals, and then we just completed the square. What square is this? If we factor y squared minus 6y plus 9, we're going to get y minus 3. I want you to pause and think about that for just a second. Make sure you feel good about that. That y minus 3 squared came from y squared minus 6y plus 9. And that factoring makes sense. Because if it does, we're almost there. Last step to get it in standard vertex form, x equals y minus 3 squared minus 3. So completing the square enables us to get this in vertex form. Let's start answering some questions. What is the vertex? Well, the vertex, if you remember the chart above, whatever makes the inside of my parentheses 0 is the y coordinate of the vertex. Whatever we see out here is the x coordinate, because x was alone on the left. If y was alone on the left, and there was an x in here, then whatever makes it 0 would be the x coordinate. So the x and y coordinates, you know, they follow the x and y variables. So that means the vertex is going to be the x coordinate over here is -3. The y coordinate is whatever makes y minus 3 equal to 0, so +3. 1, 2, 3, 1, 2, 3. I'm going to put my vertex right there. We already said it opens to the right. That's done. So it's going to look something like this. And we'll create a table here in just a second, but because of that, I know that my axis of symmetry, I'll use green, which is that line that cuts straight through the middle of the parabola, will be that line right there, because again, we know it's going to open to the right, look something like that. So what does that mean? Axis of symmetry, horizontal line looks like y equals 3. Y equals 3 is that axis of symmetry. And then how do we plug values in to make this table? That might be a question you have, because yeah, it's weird. X equals, I'll do this in black. X equals y minus 3 squared minus 3. Well, sometimes we would go x and plug x in. Let's try it. Let's plug in -2, for example. So I want to find out when x is -2, what is y? Y minus 3 squared minus 3. Add 3 to both sides. 1 equals y minus 3 squared. So square root y minus 3 equals plus or minus 1. Remember, this will not be a function. We are going to keep both values. So add 3. 3 plus or minus 1 equals y. So when x is negative 2, y equals 4 or 2, 3 plus 1 or 3 minus 1. When x is negative 2, y is here or here, which again matches our estimate of what this graph would look like. Now, we weren't asked to graph, but I just wanted to show you, we could do that again if we wanted. We could say, what if we plug in negative 1 for x? This is how you can get some values. So add 3, we get 2 equals y minus 3 squared, square root. So plus or minus root 2 equals y minus 3. And 3 plus or minus root 2 equals y. Now, I happen to know that root 2 is approximately 1.4, just about. So that means approximately 4.41 if we do 3 plus root 2, or 1.59. That's what y would be approximately at negative 1. So 4 and a little bit more. And 1 6, a little bit more than half. And we can see our parabola. So even though this didn't ask us to graph it, wanted to demonstrate that one time for you. Parabolas, we already know a little bit about them, but now we're seeing they can open left and right, and especially important, and you'll get lots of practice with this today, this right here, how to turn something from general form into its standard form. Okay, I know that's quick, but let's start talking about circles. Circles have two key pieces to them. The center of the circle, we need to know where it's centered. We need to know how big it is. What's the radius? So the standard form equation of a circle is right here. X minus h squared plus y minus k squared equals r squared, where the center is still h comma k, just like with the vertex on parabolas, and the radius is r in that equation. And that's about all you need to know about circles. We're going to do actually 4 problems with circles because circles are probably the conics that you will run across the most. Parabolas too, but circles, want to make sure you see all sorts of different types of problems. So here's an example. Write an equation for this graph, and it gives you the graph of a circle. Well, I know from above that every circle has this equation. X minus h squared plus y minus k squared equals r squared. And the good news is, as long as I know what these values represent, I can just plug and play here. H was the x coordinate of my vertex. So here I'm looking x minus -2 squared, just from the picture, from what I was given, plus y minus 6 squared, and then the radius equals 5. So 5 squared on that other side. And so we could write this x minus -2 squared plus y minus 6 squared equals 25. If we wanted, that's a great way to leave this answer. If that x minus a -2 is bothering you, then just change it to x plus 2. Nothing wrong with that. I actually kind of like the top version in the boxed answer here, because then it jumps out at me, that x coordinate's -2 there for my center of my circle. But either way is fine. This is the standard form of a circle, and I want you to look at the answer we got and see if you can reason it out to yourself just looking at that answer. Oh yeah, the center of the circle is at -2, 6, and the radius is 5. That's what you want to be able to do with these equations. All right, let's look at another problem. opposite of that problem above, and just what I was talking about. Graph x minus 3 squared plus y minus 1 squared equals 25. Well, this tells me that the center is at 3, 1, whatever makes that 0, and then whatever makes that 0. And the radius, if r squared equals 25, r equals 5, right? So if we're given the equation of that circle, 3, 1 is my center, I know the radius is 5. I'm just going to go up 5, 3, 4, down 5, 1, 2, 3, 4, right 5, 1, 2, 3, 4, left 5, and then draw the best circle I can. Always a good idea as well to kind of label things in your circle. C for center. Center is at 3, 1. And this way, if you notice, my graph is kind of off center on the page and it's not exactly on lines. Labeling just, again, provides even more clarity saying, this is what I intended. I intended to show that the radius is 5 and that the center is 3, 1. So going from an equation to the graph, another important skill. What about a problem looking like this? Write an equation for a circle if the endpoints of a diameter are at 3, -3, and 1, 5. So different type of problem, but still just going to use what we know to be x minus h squared plus y minus k squared equals r squared, our general form for a circle, our standard form, excuse me. So I'm going to draw a quick sketch. And it tells us that the endpoints of a diameter are at 1, 2, 3, 1, 2, 3. So 3, -3, and 1, 1, 2, 3, 4, 5. Something along that. That is a diameter of the circle. Now, if that's a diameter of a circle, we have an idea what it looks like. Diameter goes one side to the other, straight across. And we know that the center is well, it's in the middle of that diameter, and that the radius is that distance right there in red. So how do we do this? Well, I want to jog your memory with a couple things you actually already know. How do I find the midpoint of 2 points? Because if I take the 2 endpoints of the diameter, the midpoint will be my center. So midpoint formula, just to jog your memory, is add the x's together and divide by 2. So find the average x value and find the average y value. So in our case, that would be 3 plus 1 over 2. Again, grabbing those x coordinates from my 2 points. And then -3 plus +5 over 2, grabbing my 2 y coordinates and averaging them. 4 over 2 is just 2. -3 plus 5 is 2 over 2 is 1. The center of my circle is at 2, 1. So by averaging those x values and those y values, we will find the midpoint. And I'm going to go ahead and label these points as well. 3, -3, 1, 5. So that gets me my center. I can already start writing my equation then. X minus, it'll be a 2, plus y minus, it'll be a 1. But what is that radius? And specifically, what is the radius squared? That's what I really want. So how am I going to find that? I'm going to use Pythagorean theorem. Because I know how far across and how far up I need to go to make that a right triangle. If you look at the coordinates, I went from 1 to 2 in the x direction. So that's a side length of 1. And I went from 1 to 5 in the upwards direction. That's a side length of 4. So if I'm looking to find the radius, I can say 1 squared plus 4 squared equals r squared. From that right triangle from Pythagorean theorem. Again, knowing the coordinates, I went over 1, up 4. 1 plus 16 equals r squared. 17 equals r squared. Could I find the radius? Yes, absolutely. R equals root 17. But think about what I want in my equation. I actually want r squared. X minus 2 squared plus y minus 1 squared equals 17 for this problem. Using the midpoint formula to find the center of the circle because we knew the two diameter endpoints, and using Pythagorean theorem to find the radius, r squared, really. One more type of circle problem, and this is a good one. It says, put the circle's equation in standard form and graph. Now, this doesn't look anything like that equation we saw earlier for a circle. X minus h squared plus y minus k squared equals r squared. How are we going to put it in standard form? We're going to complete the square twice. One for the x's, one for the y's. So follow along. I'm going to try to color code this. X squared. First thing I'm going to do is add that 14x over to the left. And I'm going to say plus blank. Plus y squared plus 6y plus blank equals negative 50 plus red blank plus blue blank. Got to do the same thing to both sides if we add something. So what value would make a perfect square for my x's in red? I'm hoping if you remember completing the square from before and what we just did, you say, okay, so that'd be x plus 7 squared because it's a 14. So I need to add 49 here. If I add 49 here, I better add 49 there. What about blue? Y squared plus 6y plus 9 be over 2 squared. I need to do that. So, okay, that means x plus 7 squared, that's my perfect square, plus y plus 3 squared, that's my perfect square, equals, looks like 8, if we work that out. So what is the center? The center of this circle is going to be negative 7, negative 3, whatever makes the red part 0 and whatever makes the blue part 0. The radius, well, 8 is r squared, so r equals the square root of 8, which I can simplify. So 2 root 2. Now, you might need a calculator for this, and nothing wrong if you do. But 2 root 2, I know that square root of 2, that's one of the ones I know is like 1.441-ish. So it's about 2.82, the radius. So almost 3 for the radius, and that's enough for a sketch. I can go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3 is my center. And then my radius is almost 3, it's like 2.8. So I'm going to go almost 3 up, 1, 2, almost 3 down, 1, 2, almost 3 to the right, 1, 2, almost 3 to the left. Sketch my circle. I'm going to say that my radius equals 2 root 2, just so everyone knows I calculated that exactly, and that my center is at negative 7, negative 3. So this idea of completing the square is an important one for conic sections. It allows us to take something from general form and put it into standard form by just completing the square for a circle a couple of times. Okay, enough about circles. The biggest thing with circles that I want you to walk away from this video is that equation right there. X minus h squared plus y minus k squared equals r squared. All right, let's talk about ellipses. Again, I know we're just whipping through this right now. That's why it's called a crash course. So ellipses, there's a lot of information on the screen, and I want you to just look at it and absorb it a little bit. Right here, on the top left, we have a picture of an ellipse, and it's kind of a sideways ellipse. Notice that it's stretched sideways. It's bigger in the left-right direction. So a couple pieces of terminology. The major axis is this right here. From the long edge, kind of, well, the long diameter, I put in air quotes, the long axis that goes across the ellipse. The minor axis is the shorter one. Easy enough, major long, minor short. So over here on the top right, we have the standard forms for an ellipse. X minus h squared over a squared plus y minus k squared over b squared equals 1. Now notice bottom left, we define a couple of those things. H comma k is still the center. For all conics, we're using h comma k as either our center or vertex, kind of our reference point, depending on what kind of conic we're looking at. Now, what are A and B? A is half the length of the major axis. So A, I'm going to go rainbow pen. A is this, the distance from the center to one edge of the ellipse on the major axis. B is half the length of the minor axis. It's right here. Center to one edge on the minor axis. And so why do we have two standard forms for ellipses? Well, if the x's are over a squared, if the x's are over the bigger number, because a is the major axis, so it's always going to be bigger, then that means it's stretched in the x direction. It's like a horizontal ellipse. If the y's are over that larger value, the a's, a squared, then it's stretched in the y direction. It's a vertical ellipse. So this is why we have two standard forms. Notice they always equal 1 for an ellipse. Okay, so let's look at a few types of problems here for ellipses. This says write an equation for the ellipse that has endpoints of the major axis at 2, 2, and 2, negative 10, and endpoints of the minor axis at 0, negative 4, and 4, negative 4. For me, the first step is obvious. Sketch this out, draw a picture. It doesn't even have to be good, but major axis endpoints are 2, 2, and 2, negative 10. That right there tells us the major axis is up and down. So we know we're looking for y minus k squared over 2, over a squared plus x minus h squared over b squared equals 1. We know the y's have to come first over that larger a squared value because major axis is going up and down. Endpoints of the minor axis, 0, negative 4, and 4, negative 4. And so we can kind of see the shape of our ellipse. So to graph this, we need to know what h comma k is. We need to know the center, and we need to know a and b. Well, once we know the center, we can find the distance from the center to the edges on those major and minor axes. So only thing we need to do really is find the center. This is 2, 2, 2. This is 2, negative 10. So it makes sense that the center would be 2, something, because it's right in the middle of those. 2, what though? Well, the minor axis, we had 0, negative 4, and we had 4, negative 4. And so it makes sense that the y coordinate would be negative 4 because it's right in the middle of those. And what is right in the middle of those? 2, negative 4. We now have our h and our k. So y minus the y coordinate squared. So y minus negative 4 squared over something squared plus x minus the x coordinate squared over something squared equals 1. And remember, A is this distance from the center to one of the major endpoints. So if the center is at 2, -4, what is the distance to go from there to 2, -10? 6 units. So A is 6. And what is B? Well, B is that distance from the center to one of the minor endpoints. So 2, -4 to 4, -4, that means B is going to be 2. And now, just from kind of sketching it out and finding those values, y plus 4 squared over 36 plus x minus 2 squared over 4 equals 1. That is our final equation for this ellipse. And you can see, oh, the y's are over the larger number, so it must be going up, down. It's a vertical ellipse. The center is at 2, -4 from those numerators. And we can kind of see how wide, how tall, how long that ellipse will be. What about right here, going the opposite direction? We're given the equation. Graph the ellipse, find the center and the lengths of the major and minor axes. Well, the center looks like 2, -1 to me, just from those numerators. What makes this 0? What makes that 0? So 2, -1, I'm going to see if I can. Oh, I don't want to type. I was going to try to grab, there we go, and put this at least closer to the lattice point. So 2, -1 is my center. Now, I'm hoping you look at this and you say, well, a squared equals 49. That means a equals 7. B squared equals 36. That means B equals 6. But which way should I go? Up, down, left, right for my major axis? Which way for my minor axis? Is this an up-down ellipse or a left-right ellipse? Well, the x's are over the larger number. The x's are over 49. That means it's the major axis is in the x direction. So I'm going to go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then the y's 1, 2, 3, 4, 5, 6. So almost a perfect circle. Just a little bit smaller in that y direction. And there's my ellipse. So center is, what did we say? 2, -1. And then we're asked for the length of the major and minor axes. So the major length, and how I'm going to abbreviate that, is just a capital M length. We went 7 this way, 7 that way. Major length is 14. The minor length, and I'll abbreviate that with a lowercase m. We went 6 up, 6 down, 12. So there's the sketch of the graph, the center, and those major and minor lengths. Again, I want to emphasize, you are not expected to be an expert at this just by watching this really quick video. We usually spend lots more time going through each of these conic sections. This is just to give you an idea of some of the things out there. So when you see them in your mathematical future, you aren't completely lost. Last ellipse question. Same thing as circles. What if it's not in standard form? We have to complete the square probably twice. So let's do that. Graph and find the center and lengths of the major and minor axes. Yeah, we know that. So here's what I'm going to do. I'm going to get my x's next to each other. 7x squared minus 28x plus blank. And actually, I'm going to leave off the plus blank for now, and I'll show you why in a second. Get the y's together equals -19. Now, the reason I left off the plus blank initially is because before I can complete the square, you might remember this little fact. I need to factor out a 7 because I want it to just be 1x squared. So x squared minus 4x Now I'll put the plus blank in. Let's factor out a 3 on the y's to make it just 1y squared minus 4y plus blank equals negative 19. Complete the square, and I should put some plus blanks over here as well, so I don't forget. So b over 2 squared for red, b was negative 4 divided by 2 is negative 2 squared is 4. And remember, I'm not going to put plus 4 on the other side. I'm going to put plus 7 times 4. What about blue? Blue, same thing actually. But I'm going to put plus 3 times 4. So we get 7 times x minus 2 squared. And pause for a second, make sure that factor is okay in your mind. X minus 2 squared giving us x squared minus 4x plus 4. Plus 3 times y minus 2 squared equals 40 plus negative 19, 28 plus 12, so 21. Now, if this were a circle, we'd be pretty much done, but remember, we need for an ellipse, we need this whole thing to just equal 1, not equal 21. So I'm going to divide by 21 everywhere. And this actually works out okay because 7 over 21 simplifies to 1 over 3. So x minus 2 squared over 3, that's a squared. What does 3 over 21 simplify to? Got rid of the 3, y minus 2 squared over 7. 3 over 21 is 1/7 equals 1. And then very last step, it looks like we're in standard form for an ellipse, but we want that larger value on bottom, the a squared value, the major axis, to go on the left. So I'm just going to swap places there. Y minus 2 squared over 7 plus x minus 2 squared over 3 equals 1. And now I can see, oh, the y's are on the left, they're over the larger number. So this is an up-down ellipse. I know that the center is 2, 2, because that's what makes this 0 the x and this 0 the y. So 2, 2, I'm gonna, oh, I might have messed up. I might not be able to move my coordinate plane easily. It looks like I won't. So I'm just gonna go 1, 2, 1, 2 for my center. I need to go a squared is 7. So a equals root 7, which is going to be between 2 and 3, right? Because 2 squared is 4, 3 squared is 9. So between 2 and 3, 2 and a little more than a half in the y direction. 1, 2 and a little bit more than a half. 1, 2 and a little bit more than a half. B squared equals 3. So b equals the square root of 3, which I happen to know is about 1.7. So I'm going to go 1.7 in each direction here. And there's my ellipse. Now, as far as all the questions they asked, center we already found, 2, 2. Major axis, remember we went root 7 up, root 7 down. So major length, if we went root 7 up and root 7 down, is 2 root 7. Minor length is, and that was a 2 root 7, sorry, is root 3 to the right, root 3 to the left, 2 root 3. So major and minor axes, just making sure we kind of know what those are, what they refer to. Some people like thinking about them as sort of the longer and shorter diameters. Not technically correct because it's not a circle, it doesn't have a diameter. But if that helps you remember what it is for an ellipse, that's okay. Again, standard forms and kind of knowing what all those pieces mean will give you a good head start when you see this in the future. I'm going to grab my charging cable really quick because my tablet is low on battery. There we go. So we've talked about parabolas, we've talked about circles, we've talked about ellipses. Let's talk about hyperbolas, and hyperbolas are kind of a funky one. And so a hyperbola looks something like this. It almost looks like two parabolas. It's actually, they're not parabolas on each side. They flatten out their slope, if you will, but it kind of looks like two parabolas. And as you can see right here, we have two standard forms, one for a left-right hyperbola, where the x's come first, one for an up-down hyperbola, where the y's comes first. Now you might be looking at these equations and thinking, wow, these look pretty much exactly the same as ellipses. And you're right, they are, with the one exception of right here. It's a minus instead of a plus. And we will actually just see that when we find the standard form, when we work it out algebraically. So couple just terms, instead of a major axis and a minor axis, we have a transverse axis and a converse axis. Transverse axis is the one that transverses, cuts across from vertex to vertex in our hyperbola. The conjugate axis is the one that goes the other way, kind of off into space somewhere. So that's our transverse axis. And then right about here is our conjugate axis, going the other way in between. A is half the length of the transverse axis, B is half the length of the conjugate axis. And that should look kind of similar to major and minor. But all we're going to do today, we're going to do one hyperbola problem, and it's right here. Put this hyperbola into its standard form, and then find the coordinates of the vertices. So standard form, you guessed it, we're going to be completing the square twice, once for the x's, once for the y's. So I'm going to go 4x squared minus 32x, get the x's close to each other, minus 9y squared minus 18y. And I'm going to put the 19 on the other side, so negative 19. So factor out of 4, because I know I'm going to need to complete the square, x squared minus 8x plus blank. Factor out a minus 9, because we want just 1y squared. So y squared plus 2y, because I'm factoring out a negative 9 from that negative 18, plus blank, equals negative 19, plus red blank, plus blue blank. Complete those squares. B over 2 squared, negative 4 squared is plus 16 here. So I'm going to say plus 4 times 16. And then in blue, b over 2 squared is 2 over 2 is 1 squared is 1, plus negative 9 times 1, because that negative 9 in blue that we factored out. So 4 times x minus 4 squared minus 9 times y plus 1 squared, just factoring those, equals negative 19 plus, this will be 64 minus 9, so plus 45 minus 9, 36 is what I'm getting in my head. And then again, this looks like it'll work out nicely because we needed it to equal 1, just like an ellipse. Divide everything by 36. So 4 over 36 is 1/9. So x minus 4 squared over 9 minus y plus 1 squared. 9 over 36 is 1/4 equals 1. And there is my standard form. Just a lot of completing the square and manipulating this to get it in the correct form. Now we're asked to find the coordinates of its vertices. So to do that, I'm going to make a quick sketch. Again, it doesn't need to be pretty. But I know the center, even though I wasn't asked for it, the center looks like 4, negative 1, just from my numerators. What will make those numerators 0? So 4 comma -1 is my center. And then remember, we need to go to our transverse axis. That's the distance from the center to each of the vertices. So this is 4 -1. A squared is 9. A equals 3, right? Now, the x's are above that one. So that means its transverse axis is in the x direction. I should go 3 this way to find a vertex, 3 this way to find a vertex. So that means my vertices would be 7 -1, 1 -1, going 3 each way from the center. And so I can kind of just write that out. Vertex 1 is at 1 -1. Vertex 2 is at 7 -1. And then again, I wasn't asked to graph it, but I'm hoping, and this is maybe the first time you've seen a hyperbola, but because this is the transverse axis, it's going to look something along this line, and that is our hyperbola. This video was not meant to get you 100% completely comfortable with conic sections. It takes a lot more than this. It takes a lot more time for this information to soak in, for us to get practice. But this video hopefully does, at the very least, give you an idea of what these 4 conics are: parabolas, circles, ellipses, hyperbolas, their equations, the tendencies. H comma K is always the center or the vertex. A and B often are related to the major and minor axis, or the converse, or I should probably say it in the right order, transverse or conjugate axis. You know, the equations, if you saw something like this, say, next year on a standardized test, hopefully it would give you a shot at saying, oh, that's a circle, so that if you saw this in a question, it might ring in the back of your mind, oh, so that's a circle, center is 3, 1. That's what makes those 0, and R is 5, because R squared is 25. This is just a crash course, but I hope you found it interesting that we can make all of these shapes from slicing up cones. That's why it's called conic sections. You will probably see more of this in your mathematical future, but this is where we're going to leave it for today. If you have questions, bring them to me next time. And otherwise, I will see you later.